So in the first part of this lesson, we talked about linear relations. Okay, meaning that in a graph, it's a graph that forms a straight line, or in a table, there's a constant change in the independent variable, the first column, and also a constant change in the dependent variable, or the second column. Okay. One thing we can calculate with linear relations, and it's something that you actually already know how to do. We're just going to call it a different name. And we call it the rate of change. And the rate of change is the change in the dependent variable in the independent variable. That's a lot of words. What that really means is when we find the change in the dependent variable, which is the y's, divided by the change in the independent variable, which is the x's, that's the slope of the line. So really, this is just another name for slope. It's just with this one, we actually use units because we're actually looking at actual problems, not just a general graph where you find the slope of a line. It's some kind of problem situation. So if you remember, at the beginning of this lesson, we did the number of pizza toppings and the cost. We can find the rate of change by dividing the change in the y's. So what you could do, don't worry, I'll go back to this page. Remember, we had this table filled out. I'm not going to fill out the whole thing. Is you find a change in one pair of y's divided by a change in pair of x's. Okay, so I'm going to subtract this minus this over this minus this. So the rate of change would be 5 minus 5.75 over 0 minus 1. It's the same as finding the slope. It's basically the slope formula. So that would give me negative 0.75 over negative 1, which is negative 0.75. We can use decimals with these ones. Okay? In fact, decimals is preferred whenever we actually do problems situations. What would be the units? 7, or sorry, it's 5. What would be the units? Like, what is the 75.75? Look at the units. The cost per what? Topic. So you have to make sure to put units with rate of change. Okay? But you still calculate it the same as you would the slope. Subtract 2 y values over the subtraction of 2 x values. Okay? But then you have to express it in units. Okay? And it doesn't matter what pair we pick. We could have picked the pair down here. We will still get the exact same answer. Okay? So we can choose any pair, and it will always work out to 0.75 per topic. Actually, I could write it like that too. Instead of writing cost, I'll just put money with 0.75. And we can find the equation of linear relations using the following formula. We take whatever the dependent variable is, it will equal the rate of change times whatever the independent variable is, plus the initial cost. Okay. Again, that's a lot of words, but you know what it is very similar to? Well, remember the dependent variable is y. Rate of change is the same as slope, so that's m. Independent variable is x, and the initial amount is the y-intercept. It's the same as this. Y equals mx plus b. It's just we're using it in actual word problems now. Like before, when we use this, you don't have to write this down. You know, you would be given a graph and you have to find the equation of it using this formula. Okay? Well, now we're actually finding the equation of real life things using this formula. So going back to our example, well, what was the dependent variable? Cost or toppings? Dependent variable. Which one's the dependent variable? Cost, right? It's always the second column. The independent is always the first column. So we would say cost, or we'll call it C, equals, what was the rate of change again? We just found it above. 0.75. What was the independent variable? Number of toppings, so let's call it n. And what was the initial amount? How much did you have to pay if you didn't get any toppings? So that would be the equation of this linear relation. Okay? Very similar to y equals mx plus b. All right, let's look at the remaining examples. We did that one. We did that one. We're here. Okay. So this question is, it's asking whether these problem situations are linear relationships or not. Okay. So a new car is purchased for 24 grand. Every year, the value of the car decreases by 15%. Okay, that's something called depreciation. That's what happens to all vehicles. They go down in value. Okay. I want to know if that's a linear relationship. Well, let's do a table. Okay. Let's say year and cost. Or sorry, not cost, value. That's a better word for it. Value. So at year zero, like when we just buy it, it's worth $24,000. How much is it worth after 1 year that you own it? Well, we have to find 15% of this and take it away. So we have to do 24,000 minus 15% of 24,000. And how we do that using math, if you remember from middle school, because I believe you guys worked on percents there, is 24,000 minus, you got to write 15% as a decimal in order to do it on your calculator. This, and this is definitely a calculator question. So we're going to find 15% of 24,000. We're going to take it away from 24,000. And when we do, we should get $20,000, $20,400. That's how much it's worth after year one. So how much did it go down? It went down $3,600. The question is it going to go down $3,600 for every year I go out? Well, let's try one more year. That should be able to tell us. So remember, the car is now worth $20,400, and we have to subtract away 15% of $20,400. And when you do that, you're going to get $17,340. How much did it go down the second year? Not this. It actually went down minus $3,060. Linear or not?
No.
No. As soon as the difference are different, not linear. So we can stop. We don't have to go any further. With the second one, you can probably figure it out if you just look at the question. So an electrician comes in, they charge $75. That's just to step in the door. Okay? So as soon as they step in the door, you owe them $75. How much do you owe them after an hour? If they charge $50 an hour. How much do you owe them? How much money?
$125.
$125, right? Because you paid 75 and a 50. How about 2 hours? How much do we add to get 2 hours? You guys, it's $50 an hour. Right, so I add another $50, right? How much for the next hour? How much do I add? 50. How much for the next hour? How much do I add? Next hour, how much do I add? Is that linear?
Yes.
Yes. Okay.
So I'm just gonna say it's linear.
Because
Every hour, every 1 hour goes up by 50. So
the independent variable are hours, the dependent variable are how much is charged, and it's $50 for every additional hour. Okay, let's go to the last page. So we have two graphs. One graph is filling a water tank, and the second graph is emptying a water tank. What are the independent and dependent variables for each graph? It's actually the same for both. What's the independent variable? Time, right? It's always the horizontal. What's the dependent? Volume. That's pretty straightforward. Now, we've got to find the rate of change for each one. And I'm just going to go R of C short. And that's graph A and the R of C of graph B. Well, remember, think of it like this. It's like the slope formula. Rate of change equals y2 minus y1 over x2 minus x1. Same as the slope formula, because we agree that it is the same as slope. We just use it in a different context. So you need a couple of points. So from graph A, give me a couple of points. Give me a really easy one to work with. What's this one?
0.
Point. It's a coordinate, it has two numbers. 0, 0. That's easy to work with. Give me another point. We got a whole bunch here we can choose from. Be careful how you read them. Sorry? 21,000. Right, because it goes up by 20s on the horizontal and up by 1,000s on the vertical. So I have to subtract those two, right? So the rate of change is going to be 1,000 minus 0 over 20 minus 0. Thousand over 0 minus 1,000 minus 0 over 20 minus 0, which is 1,000 over 20, which works out to 50. What are the units? 50 what? Liters per minute, right? What are the units for rate of change? It's always the dependent variable over the independent. So what's the dependent? Liters per minute. Liters per minute. So that means that the tank is filling at 50 liters per minute. Okay? How about graph B? I need 2 points. What would you like to use?
Let's see, 4 here on juice pump.
Really, somebody can't read me one?
What's this one?
0,
6,000. What's this one? 60. Okay, so we got to do 6,000 minus 0 over 0 minus 60. 6,000 over 0. 6,000 minus 0 over 0 minus 60. That gives us negative 6,000, or 6,000 over negative 60, we could say, which is negative 100.
100? No. Yeah, 100. What are the units?
Liters per minute. What does the negative mean?
That it's emptying, right? So it's decreasing. So whenever it's positive rate of change, that means something's increasing. So this is filling up at 50 liters per minute. Whenever it's decreasing, something is losing quantity. So it's emptying at 100 liters per minute. Okay?
Okay,